Okay. I noticed on a lot of yours, you're not getting the angles. The angles of what we've been working on. All we added this time was the equations. So once you solve your equation, and remember, when you take a square root, you get a plus or minus. If cosecant is tougher to look at, take its reciprocal. Do the sign. As soon as you flip this over, what special triangle is that? 1 over radical 2? 45. So I've got a 45-degree triangle in every quadrant. So this is 4 pi over 4, 8 pi over 4. Now we talked about yesterday, every time we do one, we add 2n pi. And we can continue to give us all the angles possible ever. And n pi, where it's any integer, it could be positive or negative. If it's across from each other, if you notice here to here, it's 180 degrees apart. So at this point, we can say pi over 4 plus n pi would give me this one. So if I took pi over 4 and I added just plain old pi to this to give me 180, I convert this to the same denominator. This is giving me 5 pi over 4. So, and this angle is my 5 pi over 4. So if I get this one and add pi, I get that one. I add another pi, I come back up here, here. On the ones that are diagonal, all I have is a cycle of pi. Then you have to give this angle because you'll never hit this otherwise. This is 3 pi over 4 plus n pi. That would bring me to this one, then to this one, then to this one. Okay, so if you're going for, did I say it was 0 to 2 pi on yours? Or I said, 0 to 2 pi? So if you're going from 0 to 2 pi, you know you have 4 angles. If I was going from 0 to 4 pi, how many angles would I get? 8. So that's a good way to kind of judge what you're getting there. Don't forget your angles. Okay. Yes.
Can you do like theta is equal to n pi over 4 instead of pi over 4 plus 2?
And how would you qualify this?
Where n is any integer.
Any integer. So what if I put a 2? If I put a 2, what angle is that?
90.
So does 90 work?
No.
90 wouldn't work. If you give me n as any integer, 90 will not work. Could you give me n as any odd integer? Let's play with this a little bit. Could I do n as any odd integer? So if I get 1, 3, 5, 7, 9, would that work? That would work. That would work. But just be careful when you qualify that one. We try to keep them both the same. Either we're going to add 2 pi or we're going to add pi. But that's not wrong if you said any odd. Any integer wouldn't work. That's good that you see those, because that's what I want you guys to start seeing. Okay, so you solve your equation. Again, you take the square root, you get a plus or minus 1. So who has a tangent of 1? 45. So we got the same situation. Same situation. This looks the exact same answer as number 1. Same triangles. Agree? Okay. 41. This is the same as if you did this. And I know a lot of kids get confused when we see this. How do you solve this? X cubed equals x. You would subtract x?
Divide.
You can't divide by x. You can't take away a variable. You can never take away your variable.
So you just
Move it over. Every time you have descending values, you move it over, and then what would you do? Factor. So you're going to do the same thing here. Move the cosine over. They both contain a cosine. Factor it. If you have problems, and we put one there yesterday, with just the x's, solve it that way. Start out like this. X is equal to the cosine of x. Start out like this. And then when you get down there, and you factor this, if this is helpful, once you set all your things equal to 0, it says x equals -1, x equals +1, x equals 0. Then put the cosine word back in there, if that's more helpful. A lot of times kids get real confused when we have all these words out there, like, what should I do with all these words? Set a variable. If you don't want to use x because we're using x, use another variable. So you're factoring it. This is your difference of perfect squares. You don't have to do it that way. You can certainly do it like this. Take the square root. Absolutely fine. Either way you do it. So we have three angles here. We have a cosine where it's 0. Your cosine is your x. So here's an x value. Here's an x value. So you've got pi over 2 and 3 pi over 2. We've got the cosine plus or minus 1. Again, it's your x value. We've got this guy and this guy. You have all your quadrants here. Okay? All your quadrants. Make sense? Right? Make sure you're able to find your angles as well. The angles we've been working with, all we did was throw the equation at you this time. Okay? Now, there's a problem. I have two different variables. I have a sine and I have a cosine. So one of them has to come out. Cosine is the lowest it can be. Sine squared, however, I do have a nice little identity for sine squared. This is the one that you have to memorize. This is your Pythagorean identity. It's x squared plus y squared equals 1.
Please excuse the interruption. If there are any students who are performing this morning in the Black History Club performance, please make your way to the auditorium at this time. Thank you.
Okay, so you're going to replace this. This is your substitution. Distribute this. Now, be careful because you're on the same side of the equal sign. Don't do -2 minus 2. Collect like terms. 2 minus 2, that cancels out. Bring this guy down. You cannot factor with a negative in front of it. So get rid of the negative. You have an equation. Multiply or divide by -1. Then factor. They both contain a cosine. Factor out a cosine. From here, we have two sets of circumstances. One where cosine is 0, which we just looked at. That was your pi over 2 and 3 pi over 2. And one where your cosine is -1/2. Cosine deals with the x. So find your x-axis where it's negative. That's where your cosine of negative is. Label your triangles, find your reference angle. So this is 3 pi over 3. So I've got a 2 pi over 3, and I have a 4 pi over 3. You only had to go from 0 to 2 pi. If we went from 0 to 4 pi, how many solutions would we get? 8. Questions on this? Okay. They both share a secant, which you can't factor. You can factor it out of that side, but it's not going to help you any. But if you notice, if I replace it with like an x squared, I'd have an x squared minus x equals 2. I'm going to move everything to one side. Now I have a trinomial. If you tried to factor out the secant, you kind of got stuck after that. So think of it as x squared minus x minus 2 and factor it that way. So we have two situations. If you rather look at cosines, take the reciprocals of both sides and look at a cosine. So where's your cosine -1? At the 180, at the pi. Where's your cosine positive? In 1 and 4. In 1 and 4. Again, it's the same cosine we just saw before. So reference angle 60. Are we getting this? Everybody's good?
Wait, so it'd be pi over 3, 3 pi over 3, or 5 pi over 3, and 3 pi over, or pi.
Pi. Just 3 of them. Try to kind of loop your ones over here. They're kind of looped together. I only asked you to go from 0 to 2 pi. Sometimes we say 4 pi, sometimes we say all solutions we have a little variety. Okay? Now, this one, if it looks weird, stick variables in here. xy equals 2x, what would I do? If this says xy, and I make my cosecant be y, and I have 2y, what would I do? Can't divide by y. Move it over, factor out your y. So move over your cosecant, factor out your cosecant. Your goal is to make two separate, the same thing when you take a binomial, a trinomial, and you factor it to two binomials and you set them equal to 0. It's the same concept. But by separating them, they can have two different functions. So we've got a cosecant of 0. Now, if you remember your cosecant curve, okay, it goes off of your sine curve. Isn't your sine 0 at the 0? So we can't, when we flip that over, we're not going to be able to get a cosecant. Because it was your zeros that gave you trouble. And the other guy, if it helps you, flip that over. Cosine, where's cosine positive? Again, we see the same kind of triangles. These are your special triangles. So everybody can do this. Okay? This one's kind of messy looking. I've got a sine and a cosecant. But my cosecant is the reciprocal of sine. So I replace my cosecant with the reciprocal of sine. They have nothing in common. It's like an x and a y. But luckily this one flips into this. That's its reciprocal. Put everybody over 1 and multiply by sine and get rid of the fraction. And then again, you can solve it. Subtract 1, divide by 2. When I take the square root, you can't because it's negative. No solution. I could take the square root of 1 over 2, get the plus or minus, but I can't take the square root of a negative.
These last two items.
Okay, now remember yesterday I went over that identity and I kind of hooked this guy up together. You have cosine squared plus sine squared equals 1. So in order to get tangent, out of the cosine and the sine, how can I get a tangent? Divide by what? If I divide by sine, I get a cotangent. So what am I going to have to divide by? Cosine. I want a tangent. So tangent is sine over cosine. So I get 1 plus tangent squared equals secant squared. Okay. Now, you're going to have to play with this a little bit. I can move this over here. I can make 1 equals secant squared minus tangent squared. But that doesn't give me this guy. Right? Because this is secant, and it's not even a square, and I absolutely can't take the square root of 2 terms. So I have to leave this one here. But I notice the same words, secant and tangent, are over there. So you have to kind of play with this one a little bit. So if we replace this guy with a 1, there's my 1. I replace this guy with a 1. We put your secant and your tangent in. Okay, you got to kind of like mess around here a little bit.
Wait, where'd you get the 1 from?
The 1, this 1, I replace this with. Okay. This.
Yeah, but how? Oh, I see.
Well, I multiplied. I want to get this. I want to keep this 1 out of here.
Yeah.
I can use that, but I can't use this. So if you multiply by this, you're able to get that 1 out of there and get this in there. You can't get that right now. So if you
multiplied
take
the
this
whole thing
by,
by, oh, okay.
I want that 1 back. I want to get that 1 back in here somehow. So I can take this guy, I might have switched these around. Multiply this. This has got minus in here. That's what's confusing you. So if I multiply this guy by this, I get, this is my difference of perfect squares. I can now get that guy and replace that with a 1. If I multiply this side of the equal sign and this side of the equal sign by this factor, I can now get this piece that we just did over here and replace that with the 1. Substitute it out with the 1. This should have a minus in it.
Okay.
Do you see what I'm saying? Okay. There's nothing we can do with your secant and your tangent. We can't take the square root of these guys. So if I can somehow get a secant squared minus a tangent squared, I can get a 1 out of that. And I can use secant and tangent and replace my secant and tangent and figure out what I need to do. So if we multiply this side and this side by its perfect square factors, you know your difference of perfect squares? Essentially, that's what we're doing. This one was hard to see. I kind of put parentheses so that you would leave that as a factor. I thought maybe that would kind of help. It is a little bit, difficult to see this guy. So now when we get here, let's see where I am. We multiply this guy here. Okay, so we took the 1. And secant. I get rid of this one in here.
Okay, I'm back to being confused.
Okay, so here, you gotta kind of just follow this for 1 second. We replaced this guy, right?
Yeah, I
All right,
understand that.
now, we got to this part right here. Because we brought this, we multiplied 1. Then, this is very confusing, this guy was also equal to 1. Just don't put it there. This guy is your original equation. Secant x plus tangent x equals 1. So therefore, substitute the 1 for secant x plus tangent x.
I thought it was secant.
I thought it was tan squared.
Yeah, you're right. That's our identity. But look at your original problem. What does your original problem say?
Okay, so
Secant x plus tan x equals 1.
we multiplied by secant x minus.
Yep. We did. And we got this.
Yes.
Okay? Now, this is where our 1 comes in.
Yes.
Now, our original problem says secant x plus tangent x equals 1. So now, can I put this guy back over here in place of this? Can I take this 1 out and put this piece in here?
Yeah, but why would you want to?
Because I need secant and tangent to be together at the same time. I need secant and tangent to be together. So now, look what I end up with. So, won't my secants cancel out?
And so
And so my tangents, no, not my tangents, because
Oh, no,
I'll get
no,
tangent
okay.
squared. Tangent squared is equal to 0. I just didn't write this.
wait, I thought it was just two tangent.
Yeah, right.
2 tangent, 2 tangent. 2 tangent. And if I say 2 tangent divide by 2, then my tangent's equal to 0. This one is a tough one. I tried to... Oh, I wouldn't give you, I don't think I would give you this one. I tried to leave the parentheses around here to kind of give you like a grouping feeling, but you got to do a lot of playing around with this. You have to see that tangent and secant have to be in there somewhere. So if we replace this 1, and I should have put this on this side, but switched them around. This is where this 1 comes from over there. This guy says, okay, now give me my 1 here, bring this down, but oh, my original equation says this. So if I take the 1 out of here and now replace it with this piece, I've got the same variables. I've got an x and a y. It's almost like when you do a systems of equations and eliminate one variable. We're kind of trying to eliminate one. So when I get down to here, I just moved this down, but it looks confusing to put it here.
So all that work is basically just like to prove why you ended up putting them
Well,
together.
to get what we get here. If you're not getting this one, it doesn't upset me. There's a lot of things going on here. As long as you can do this part, that's probably in the next one, isn't it?
But I get it now. I get it now.
It was a little bit
It
difficult.
was just weird, like,
Mm-hmm.
but I understand.
Okay. Okay. It's a lot of moving and manipulating. This guy was probably a little bit better. This one uses your identity a little bit better. The same identity that we just did. So this one might be a little bit easier because they both have squares in them. So I left them alone. So if you want to replace one of these with the other, it doesn't matter which way you go. I just happen to go with this, replace my secant squared. If you replaced your tangent squared with the secant, you could do that too. So I replaced this guy. The one thing that you guys have to be aware of, and I see this all the time, you're on one side of the equal sign. Don't do this. You're on one side of the equal sign. So this is where you combine like terms. If you do that, you probably won't be able to factor it. So this comes out to be your -1. So 3 tangent squared plus 1 gives you 1. 2 tangent plus 1 tangent gives you 3 tangent. Divide by 3. That should look like a familiar a side of 1, a side of radical 3. That's a triangle, we know. That's your 30 degrees. And you're in all 4 quadrants. Is that a little better? Using it, the identity this way.
Yeah.
This one I would give you. The other one is a tough one. Questions on this at all? Everybody can do this.
Yeah.
Okay. So I've got a multiple angle. This is where it's different, right here. But I'm going to solve it as if it's a regular angle. I'm going to solve it for 3x, as if it was x. So what should I do first? Add 1 and then what?
Divide by 2.
Okay. Now, you're going to solve this as if it's a regular angle. And what we're going to do is we're going to do any solutions first, and then we're going to find all solutions in 2 pi. But the key is to find your all solutions first. So, where is my cosine positive? 1 and 4. It's wherever x is positive. So cosine, and this is your radical 3. What's that reference angle? 60. So what's my solutions right now? Pi over 3 and 5 pi over 3 plus 2n pi, where n is any integer. Sorry? Yeah, not yet. Not yet. First we solve it as it's a regular one. Okay? Now, row 1 notice, okay, we solved it as if it's 1 unit, x, but it's really 3x. I have a multiple angle. If I have a multiple angle, do I get more angles or less angles? More angles, right? For every 1, I should get how many? 3. So if I have 2 in 2 pi, if I have 2 solutions in 2 pi, how many solutions should I get in 2 pi? 6. So now I'm going to take my 3 and put it back here. Okay. I'm just going to bring my 3 back here. So now I need to solve for x. I'm going to divide everybody by 3. All these parts here by 3. So this is going to come out to be x. This, pi over 3, divided by 3 over 1, says keep change flip, says pi over 9. With me? Divide this guy by 3. And keep the same, n is any integer. So my pi over 3 went to pi over 9. Okay, good so far? And this is your any solution part. We're going to work on the solutions between 0 and 2 pi in a second. Do the same here. So x is equal to, you tell me.
1 pi over 9 plus 0 pi.
Okay. And again, this is where n is any integer. It's that simple. We don't have multiple angle formulas. We just take the angle, we find where it would be, and then we make multiple angles out of it. If it's a half, we keep the half, and then when we get here, to get rid of the half, what would you have to do?
Wait, what?
If this was a half, and we're here at a half, you have to multiply by 2, right? So if you have half the angles, it's going to take you twice as long to get through your regular angles. So you're going to multiply. Now, here's the tricky part. From 0 to 2 pi, I need to make myself go here and keep adding 2 pi over 3 until I reach 2 pi. So I need to take my largest denominator and convert everybody to the same denominator.
The largest?
The largest number.
Okay.
So I'm going to convert this to ninths. It's easier to convert this one too, because then you know where to stop. We counted, we know we should get 6. So this would be 18 pi over 9. So this you have to keep the same denominator if you want to add your fractions. So what would this be? Times 3 times 3.
7 pi.
So every time we're going to do this, we're going to add 6 pi over 9. So here's my angles. Pi over 9, add 6 pi, 7 pi over 9, add 6 pi, add 6, 13 pi over 9. Did I reach 18 yet? Not yet. Add 6, what do I get? 19. I'm past the 18. So I'm out of my where I want it to be. So I stop. Then I come down to this guy. I do the same thing. 5 pi over 9. I can convert this, but I already converted it up here. So add 6. What do you get? 11 pi over 9. Add 6. Oops, sorry. 17. 57. So I'm still within the 18. If I add one more, won't I be out of the 18?
Yeah.
How many angles did we get?
6.
6. How many angles did we say we would get?
6.
6. So when we do multiple angles, we solve it as this is a regular angle, and then we take care of the multiple part, the multiplicity part. Okay? Always do this first. Even if it says to you just go 0 to 2 pi, do this first. Let's see if we can start this next one. I think this is a half one. It works the same way, just the opposite part. Okay. If it helps you, if this is a half, this is a half x. So let's solve with that little piece in the middle. So you're going to subtract 3 and divide by 3. So what are you going to get? Negative 1. So, where's tangent negative? 2 and 4. And what reference angle do we have? So, what's your angles? This guy is 3 pi over 4. And what's this guy? 7 pi over 4 plus 2n pi plus 2n pi. Okay. Now,
Wait, wouldn't it just be n pi?
okay, so let's convert it. So let's start like this, and now let's convert it. You're one step ahead of me. So before we take a look at my 1/2, again, since we're across from each other, we can condense this. So which angle should I start with? 3 pi over 4 plus what? And now just say n, any integer. I could say it up here too, but I was going to change this, so I just didn't say it there. Say it just once somewhere. Your n is any integer is not going to change anywhere that you go. So as long as you say it at the final one, I'm okay with that. Now, let's deal with the 1/2. I need to deal with the 1/2. So to get rid of the 1/2, what should I do? Multiply everybody by 2. This guy, this guy, this guy. So this becomes x. What does this become? 6 pi over 4, which reduces to 3 pi over 2. You can start with 6 pi over 4. Just write that out and then reduce it. Plus 2n pi, where n is any integer. Okay. Now if you're going to add 2n pi, what denominator do we have to convert this to? To 2. So this becomes add 4 pi. Right? And we're going to go from 0 to 2 pi. Convert this guy to 2's. We need to go to 4 pi. So if I get 3 pi over 2, and I add 4, what do I get? 7 pi over 2. Am I past that? If I convert this?
We're going to 4 pi.
Oh, this one said 4 pi? Okay, because this one wouldn't work in your 2 pi. And doesn't that make sense? If I went to 2 pi, and I have 2 angles, if I take the half angle, shouldn't I only get 1?
Yes.
So in 4 pi, shouldn't I get 1 more? Went to 4 pi, sorry. 8 pi over 2. Okay, so work them like you normally work them, and then at the end, put the piece in there. If it's a number greater than 1, you're dividing each part. Divide each part. If it's a number less than 1, a fraction, you're multiplying.